someone in the chat. Yeah, so here we can response. When you click it, right, you can use this part. Maybe this one work as a right hand.
Oh, this part, okay. Yeah. Hello. Hello. Can you hear me? Yeah, okay. So I will start the class now. So what I plan to do is I will go through the summary sheet, and then and there I will go to the topic sheets. Since 2 hours, it's we have to rush to finish all the 9 topics. Okay, then. So can you see this screen sharing? Can you see the screen? Yeah, okay. Yeah, so we start from here, and so here how to distinguish continuous times and discrete time signals. So continuous time means in the time axis it is continuous. Yeah, time axis it is continuous, and so that continuous time variable, if it is a temperature, then temperature exists for every second, so every fraction of seconds. But discrete time means if stock market price is, then that is for a certain, if the exchange rate it is per day, so or the average temperature per day, then that is actually discrete. So that is the analog and discrete. And how to distinguish between differential equations and difference equations. So that also, you know, differential equation, that is with derivatives, and difference equation, you have the difference. So if it is d by dx, so dt, then that is actually the differential equation, and that becomes xn minus xn minus 1. That is the difference equations. And manipulating discrete time signals and unit impulse response, so that you should be familiar with that one. So for example, so if you are given a signal like this, n minus xn is something like this. Let's say this way. Then if you want to have it like x some shifted signal, some x minus 5. So here this is 0, this is 1, 2, 3. So what you have to do is this one and this one has to be the same pattern. So that means here n equal to 0, this is 0. So here n equal to 0 means n equal to 5. So at 5, that is the 0. So at 5 it is 0, then this one. Likewise, okay. So if x minus n, then you have the, because minus 1 is actually plus 1 is minus 1, so it is actually a flipped signal. Likewise, that is the manipulating discrete time signals. And then definition of continuous Fourier transform, that is okay. Continuous time, discrete time. So this the other thing is so discrete time frequency. So always it is the theta, that is 2 pi f analog frequency divided by fs. So that is the discrete time frequency. The unit is radian. And then the relationship between analog and digital frequency, the period. So the period, discrete time period. So if you have a sinusoid signal, sine 2 pi or sine, let's say sine pi by 2 n. So if it is periodic, then it has to be sine pi by 2 small n plus capital N. So these two has to be equal. We should be able to find the integer value. So here n has to be integer. N has to be integer. N has to be integer. You should be able to find an integer value. So here whether we can find it, we can check it. So here pi by 2 capital N, that has to be multiples of 2 pi k, because sine, we can add any 2 pi here. So here we can add any 2 pi. So that means here what is the n? So is there someone in chat? Yeah, okay. So then n equal to how much? 4k. So yeah, 4k. So for what is the for minimum value of k equal to 1, we can find the period 4. So that means this is periodic with 4 samples. Okay, so that is this one. And then number of samples, that is okay. Block diagram of conversion from analog signal to digital signal, and to form so to convert analog signal to digital signal. So what you have to do is first you have the analog signal, so it is xt. So finally xn. So the end signal is xn. What are the things you have to do? So first this one, sample and hold. So you have to have the sample and hold. So it's kind of a switch. Yeah. So it's kind of a switch. And it says take the signal, and you know fs equal to fs has to be greater or equal to 2 times of f max. So what we have to do is we have to remove anything higher than fs by 2. So then that means we need to have an anti-aliasing filter with a cutoff frequency of fs by 2. Then we have the sample and hold. Then we have to have the quantization, because the output of this one is again analog value. So it's but we have to define a quantization scheme. So based on the number of bits. So if it is 3 bits, then we can only have 8 different possible values. So based on that one, we have to define the quantization scheme, and then we have to find their values. Then so that is the quantization, then encoding. So the last block is encoding. Encoding means for each level you assign a bit sequence. So some kind of bit sequence. Some kind of, likewise you have the bit sequence. So xn will be just a bit sequence. So that is the block diagram's representation of analog and digital conversion. Then sampling of analog signals, Nyquist sampling theorem and the limitations. So that means here, yeah, so the other one is, so as I told you earlier, so when we sample it, maximum frequency we can have is only up to fs by 2. So if there is any signal higher than that, then that is going to get aliased, because the analog signal, let's say this is the spectrum of an analog signal. So let's say this is 500 hertz. So then when we sample it, this is the spectrum of analog signal, X analog, F. So when we sample it, what is happening is it is going to get repeated. So let's say if we are sampling at 1000 hertz, so Fs equal to 1000. So that means this spectrum is going to get repeated at every Fs. So this is 500, then at 1000, again the same spectrum going to repeat. Then at 1500, it's going to repeat. And the same thing at the negative side also. So it's keep repeating. So that is the digital spectrum. So this is XD, digital spectrum. Okay, so I put it in the hertz scale, but we should usually draw it in the theta scale. Theta, so every values you will have to find it theta. So every value 2 pi, whatever the analog frequency divided by Fs. Okay. So, but let's say if you sample it at lower sampling frequency, so let's say if you sample it at 800 hertz, then what happened is after 400, it is going to only up to 400 it is going to capture. Okay? Only up to 400. So this is 400. Then what happened to this other signal? So other signal going to get aliased here. So it is going to get aliased here. So this triangle actually equivalent to this triangle. So when we have this one here, so this is equivalent to this one. So the area and everything is equivalent to this one. So what happens is the sample spectrum will looks like, so 100 hertz. So this is 400. So this is 300. So 400 up to 300. This will come here. Then it is flat up to 400. Okay. Likewise. So it is something like up to 300. It is coming down like that, and then flat. Okay. Why it is flat? Because this part, the up to 400 to 500 hertz, that is actually get aliased to 300 to 400. So between 300 and 400, this point is 300 hertz. So from the 300 hertz to 400, this is the alias part. So then this spectrum is going to repeat. Likewise, okay, in the negative side also. So this is what aliasing. So this part is aliasing. Okay. And how do you find alias frequency? So every frequency here you can find it with this equation Fk. So what you do is so every frequency you subtract Fk equal to F0, whatever the frequency, minus k times of Fs. So you keep on subtracting it until it becomes, it falls between minus Fs by 2 to plus Fs by 2. So until it falls within this frequency, you keep on subtracting it. So you get the alias frequency. Okay, so that is aliasing, and Yeah, so that's finished the topic 1. So we will move on to topic 2. Yeah, so sampling bandpass signal. So the special case of this bandpass sampling is, I told you that we have to get twice the maximum frequency to sample it. So here, what we have is, let's say if we have a bandpass signal, let's say from 3K, 2K, 4K. From 2K to 4K, we have a signal. Then we don't necessarily take higher than 8K as the sampling frequency, because what we can do is, even when we have is as fs equal to 4K, what happens when fs equal to 4K? What is the frequency where this 2K is going to fall with this equation? We can calculate it. So 2 if 2K, the 2K frequency dash equal to 2 minus K times of fs. So that is actually minus 2. Sorry, yeah, minus 2. Okay, and so if we have 4K as the sampling frequency, 2, yeah, so it is centered at 2. Yeah, let's draw a diagram like this. It's easy. So if we have 4K, then 2 to 3. Yeah. Let's have it from 2K to 3K. So what we want is finally like this. Okay, 2 to 3. So this one, 1 kilohertz. Okay. So then what we can do is, if we keep the sampling frequency as 4S, let's check the nodes. I think there's a question here. Yeah, okay. So it's actually 2K is enough. So if we have the sampling frequency here, this is the bandwidth. Bandwidth is 1K now. So we can have with 2K, twice the bandwidth, 2K, we can actually bring it to the baseband. So why? Because with 2K, we can find what happened to this 2 kilohertz, 2 becomes 0. So this point is going to come here. And then the 3 kilohertz point, if 3 kilohertz point is going to be 3 minus that 2 times of K. So that means 1. So that is equal to 1. So this point is going to come here 1. Okay. So without any distortion, we get this signal from 0 to 1. So for this band pass signal, since we don't have any signal here, That is why otherwise it will alias. If we have something here, then it will get alias. Since we have only bandpass signal, then this one is okay, the sampling frequency. Okay, so this is kind of a special case. Okay, then topic 2 summary. Yeah, so bandpass signal and block diagram of conversion from analog to digital. Analog to digital and back to analog form, including the block diagram. So I told you the analog to digital, and let's see what happens with digital to analog. So digital to analog. So here you have the digital signal. Digital signal means it's actually some numbers like this, and finally you will have to let's say some kind of this signal. So then finally you have to get the analog signal. Okay, how do we get that one? So the first thing is what we have to do is we have to pass it through a D2A converter. So what D2A converter do is it actually convert with the pulse. Okay, so it do a convolution with the pulse. So what happens to this one is it becomes it's kind of a staircase function. Why? Because these two are convolution. Convolution, you know, you flip this one and then move along this one. So when you flip it and move it, so it traces this value to this one. So this is actually the convert signal. Then what you have to do is you will have to pass through a low pass filter. So reconstruction filter. And reconstruction filter cutoff frequency again has to be fs by 2. Then after the filter, what happens is it actually gets smooth like this one. Okay, it gets smooth. These points it gets smooth. Likewise, it is smooth. Okay, so one interpretation is what happens in the low pass filter, because you know, in the Fourier transform, you know what is the for sharp edges, what is responsible for sharp edges? It is the high frequency. So all the high frequency contents are removed. So it traces the envelope. So it traces the pattern. So that is the analog signal. But in the frequency domain representation, what you can think of is, let's say, so earlier analog signal, the spectrum looks like it's kind of a repeated spectrum. So it's repeated spectrum fs by 2, and here fs. Likewise, it is a repeated spectrum. Then, but our analog spectrum is only this one, fs by 2 minus fs by 2. Okay, so simply how can we do this one, this conversion? We pass through a low pass filter. So you imagine that you put a low pass filter here. So when you put the low pass filter, then you get this one. So what is the cutoff frequency of that low pass filter? Low pass filter. So that is this fs by 2. Fs by 2. So with fs by 2 cutoff frequency, you can take out this one. Okay. But as I told you earlier, here we have this one, this convolution. Because of this convolution, so what happened, the convolution in time domain convolution, what is in frequency domain, it is the multiplication. So here what you do is, in the xn, you do the convolution with this pulse signal. So in the frequency domain, what happens? Frequency domain, you have this signal multiplied by the frequency response of this one. Frequency response of this one is this one. And the frequency response of a pulse signal is, what is it? It is the sinc function. Okay, sinc function. So you multiply these two. So when you multiply, what happened? You have this pulse is the dominant pulse. So that keep this one, but these things get smaller, but still there's a effect, like there's a so you have this pulse, this signal, this one multiplied by the sinc function. When you multiply with this sinc function, likewise, so what happens is these get distorted. Some kind of a distortion is there. Some kind of distortion. Okay. So that is the sinc function, what is sine x over x. That is sinc function. So this distortion is sinc distortion. So how do we avoid this distortion? What you can do is, before sending the pulse here, what you can do is you can multiply by the digital signal, you can multiply by sine x over sine x. Then you remove this distortion. Okay, so that is about digital to analog conversions. And then analog to digital, in particular, amplitude quantization and quantization error. So this is about quantization. So what is quantization? As I told you, it's based on the number of bits. So let's say you have 5 voltage, plus or minus 5 voltage. Then what you have to do is from plus minus to this part, you will have to divide it into that number of divisions. So let's say B is equal to 2, then how many points you can have? 2 to the B points, that is 4. So you divide this one into 4 points. Okay, 4 divisions. So this is one quantization level, this is second quantization level, third quantization level, fourth quantization level. So these are the quantized values. So this is value, these values are the ones, let's say this is 2.5, so 1.75. This is 2.55, so this is 2.5, 1.25. So this is 1.25. So this one will be 3.75. Okay, so these are the quantized values. So let's say you have an analog value of you have this sinusoid signal and this sample point. This point is let's say 3.5678, something like that. So after quantization, this one 3.56, where it falls in this window. So you, after quantization, you assume it as 3.75. That is the quantized value. Okay, and what is the quantization error in this case? So this is actual minus quantized value. So quantization error is equal to 3.5678 minus 3.75. Okay, likewise. So what is the maximum quantization error you can have? Maximum quantization error here is how much you get? 1.25. This is the maximum. So that is delta V divided by 2. So here it is 1.25. Okay, so that is the maximum quantization value. And then you have this quantization error. This is the quantization error. Okay. And then the quantization error is actually distributed into a normal distribution. Normal distribution means all the error values are equally possible. So since all the values are equally possible, so this one is from here, that is the 1 over delta V. I think. So these things, maybe I will go to the notes and quickly go through. Topic 1. So yeah, so here quantization error. Yeah, so this is what I told, and here this is the maximum quantization error, that is delta V by 2, and then you have the distribution. So this is the distribution, you have it. Here this is the distribution. Distribution. Yeah, okay, so so this is the distribution. So in this distribution, the probability is this one, and with this probability, you can find the quantization error. So quantization error is delta V squared by 12. And for sinusoid signal, when you put the sinusoid power equal to sinusoid square power for sinusoid signal, what is the power? A squared by 2. When you substitute that as the power, the signal to quantization noise ratio, you can get it as 6 points. Yeah, that may be in the next slide. So that is for the sinusoid cases. For general case, this is how you get the quantization noise power with the equal distribution of probability. The minimum error is minus delta V by 2 to plus delta V by 2. Okay. So that is, and for sinusoid signal, you get this equation 6.02 plus 1.78. So when you substitute the sinusoid power here, okay. So that is about quantization, and then analog to digital roll of that we finished, and definition of discrete time signal and block diagram. Draw the block diagram, how to differentiate between discrete time. Yeah, so then this about the systems. So far we studied about the signals, then the systems. So discrete time system is represented by basically 3 elements. One is a multiplier, adder, and the delay element. So any system you can represent like this. So so for example, any system you can represent. So this is the delay element. So 3. So what is the equation for this one? So it's set equal to, if this is 1, 1 plus 3 set to the minus 1. Okay, so likewise you can write all the system equations, and the system is classified as 3 So four categories. One is static. Static means you don't have any memory element. So it has to be only xn. There shouldn't be any xn plus 1 or xn minus 1. That is static. And time invariant, time invariant and linear system, I'll come back later. Causal. So for causal signal, you should not have any future signals. So you should not have any future signal. So it has to be present and past. And stable, so stability, that impulse response has to decay. Okay? And stability, now later on you studied that all the poles has to be within the unit circle, so that ensure the stability. For linear time invariant and linear system, let's see. So time invariance, what you do is, let's say you have a signal xn equal to nxn, yn equal to nxn. Yn equal to nxn. So time invariance means first you delay the input, delay xn, delay the input, okay, delay input. So that means xn becomes x n minus 1. So you are delaying input. So delaying the input. So when you delay this input, let's say you have a y dash n. So y dash n is you delay, you keep it this one, n, delay the input n minus n naught. So n into x n minus n naught. Then that is first thing. Then the second one you have to do is delay output. So this is a function of output. So delaying output means replace n with n minus n naught. So wherever you find n, replace it n minus n naught. So that becomes y n minus n naught. That is equal to n minus n naught into x n minus n naught. Then you check whether these two are same. Here, this is not equal to y dash n. So that means it is time variant, time variant, okay, time variant. So that is how you check the time invariance. And for linear system, that is very simple. So how you check is you scale it, scaling by let's say axn plus b x1n plus b x2n. So you can check the scaling or the addition. And if both of them works, then it is linear. If one of them doesn't work, then it is nonlinear. Okay. So that is for linear systems and stable. And then interpretation of discrete times weighted sum of delayed input, understanding the convolution, hand and graphical convolution. So convolution, I think you know convolution. So what happens for the convolution? So Hn, so what is Yn, the output of a system, Yn, Hn, it is, sorry, this is Xn. Here Xn, the output is Yn. So what is Yn? Yn is equal to convolution of Xn, convolution of Hn. So how do you do the convolution? Let's say if it is Xn is something like the Xn is something like, so Xn is something like 3, 1, 2, and if Hn is 1, 0, minus 1, so then how do you do the convolution? Or 1 plus 1, let's say put some two values, let's say 1, 2. Then how do you do the convolution? So first you flip it. So 3 time domain convolution. So likewise you do, and then 1, 2, you flip it. When you flip it, what happens? This 1 comes here and 2 comes here. Then you move this one along this line. Okay? So when this comes just under this one, 2, 1, what is the answer? Yn? Yn is equal to 3 plus 3 into 1, so 3. Then 2 into 0. So then this 1 comes here, 2 comes here. So 1 into 1, 1, 3 into 2, 6, 6 plus 1, 7. Then this moves 1, 2. So now it is 2 plus 2, 4. Then it moves here, 2, 1. So 2 into 2, 4. Then it's zeros, likewise. Okay, so that is the time domain convolution. Also, you can do the frequency domain version also. If you are in, there are two methods. One is you can do the time domain convolution. The other one is the frequency domain convolution. So frequency domain convolution, what happens in the frequency domain? What happens in the frequency domain? So this one. So what happened? 3, 1, 2, what happens? Xn becomes Xn 3, 1, 2. So you can take the Z transform of this. So how do you take the Z transform of this one? Xz. How do you write? So if you actually properly want to write this one, what is the way to write this one? 3 into delta n. That's delta n minus 1. That's 2 into delta n minus 2. Okay, so what is the Z transform of delta n? 1. So 3 plus Z to the minus 1 plus 2 Z to the minus 2. Then Hn also you can write that one. Hn also you can write Hz. Hz 1, 2. So 1 plus 2 Z to the minus 1. Then Yz, how you can do is Yz equal to Xz multiplied by Hz. Why? Because time domain convolution is frequency domain multiplication. So you can multiply it and then you can do the inverse Z transform. Then you will get the same answer. Okay, so that is the way you can do it in the frequency domain. Okay, so we will move on to the next one. So impulse response of a linear time and how to calculate it from a difference equation. Yeah. So the other thing is, so impulse response. So impulse response, frequency response, and difference equations, and transfer function, pole zero diagram, pole zero. So any of these things, if you know impulse response, then you should be able to write the difference equation. You should be able to write the transfer function. You should be able to write the draw the pole zero diagram. You should be able to find the frequency response, everything. Likewise, if you know the difference equation, from difference equation, you should know how to write the impulse response, how to write the pole zero diagram, how to write the transfer function, how to get the frequency response, likewise. Okay, even from transfer function, you should be able to draw the pole zero diagram if you are given this one. So you should know, if you are given one of these things, if you are given one of, not this one, one of these, if you are given one of these things, then you should be able to find all other things. Okay, so I will just take one impulse response. So let's say Hn. If Hn is Hn, if Hn is given as 1, 2, then you can find Hz, that is 1 plus 2 z to the minus 1. You can find the difference equation. What is yn equal to 1 plus 2x n minus 1. And you can find the frequency response. The frequency response h theta. You can h theta, how do you find it? Z equal to e to the j theta. So 1 plus 2 e to the minus, e to the j theta, yeah, e to the minus j theta, likewise. And then from here you can find the magnitude response, h theta, magnitude response, and phase response. Then what else you should be able to find? Pole zero diagram. You can draw the pole zero diagram. So for this one, so how do you get the pole zero diagram? So 1 plus 2 z to the minus 1, so that is equal to 0, z equal to 1, z equal to minus 2. So you have a, so 1 plus 2 z to the minus 1 equal to 0. So that is minus half. Z plus 2 equal to 0, z equal to minus 2. So you have a 0 at minus 2. Okay, likewise, 0 at minus 2 and the pole origin at pole. Okay, so you can, so from this one you should be, you can find this one, this one, this one, and this one. Okay, and the other way, if you are given the Z transform, you should be able to find the impulse response, you should be able to find the difference equation. Likewise, if any of these, just make sure that if one of these are given, then you should be able to find all other things. Okay, so that is about this one, and calculated from the FARIR, in particular the impulse response, discrete time convolution, properties of Z transform convolution. Yeah, so then the Z transform, you should be able to find it from the first principle. If you have to find it from the first principle, Z transform. So if it is from the first principle, then xn e to the, sorry, not e to the, z to the minus n for all possible infinity to plus infinity. So that is from the first principle, but you don't have to. So if you are only asked to use the first principle, then you have to do it. But otherwise, what you can use is you can actually use these Z transform tables, and you should be able to apply the Z transform table. So have I missed anything? Yeah. So you should be able to find these properties. You should be able to find, apply it. So basically, you should be able to apply this table. So if you find this pattern, you should be able to apply this pattern likewise. So that you should know. And this for symbol signal, these are the symbol signal. The unit impulse, the transform is 1, unit step function is 1 over 1 minus likewise, and these are the properties. So okay, so that you should be able to apply it. And B2 that transform application, and given the impulse response of 2 cascaded system, be able to compute the overall. So if 2 cascaded system, then you should be able to calculate the that is again the multiplication. So if it is H1n here and H2n, then the overall function is H1 convolution H2. Okay, and in the Z domain, it's 1Z multiplied by H2Z. Okay, so that is the multiplication in frequency domain. Okay, and that's with the with the third one. So how to find the inverse set transform? So when you are to find the inverse set transform, again, what you have to do is you will have to break that into the pattern. So in the table pattern, that's one thing. The other one is the you have to use the partial fraction. So let's say 1 plus 3Z plus or 4Z plus 3. So then how you can do is you can break it into a partial fraction. 1 plus Z to the minus 1. So here if you write it in the Z pattern, the Z, so it is Z squared. Let's say this one yeah, so let's put it here Z minus 1. So here it becomes Z over Z squared plus 4Z plus 3. So then what you do is you do a partial fraction. Okay, so what is the factor of this one? Z plus 3A plus Z plus 1B. Okay, then you should be able to calculate A and B. Okay, so how do you find A and B? So there's a shortcut to find A and B. So for the cover-up rule, so what you can do is this one you can write it as this part. So this one you cover up in this one. So here let's say this one you can write it as Z into 1 over Z plus 3 Z plus 1 equal to Z plus 3 plus Z plus 1. So what you can do is for this one, you cover up this one. So you cover this one to find what value here. You cover this one and then you cover this one and then you substitute whatever that makes this one 0. So Z equal to minus 3. So replace Z equal to minus 3 here. So that is 1 over minus 3 plus 1 minus 2. And here what you do is here you cover this one. So for this one, you cover this one and substitute for the rest, whatever that makes this one as 0. So minus 1. So minus 1. So 1 over minus 1, 2. Okay. So that is the shortcut. Then you can write the inverse Z transform from the table. So this becomes, so you already have a Z here multiplied by Z here. So that means it is these things like becomes this Z when you multiply inside, it becomes 1 over 1 plus Z to the minus 1. So that is actually in this pattern. Okay, A and UN pattern. You can write it. So that you can write it as xn. You can write it as minus 1 by 2 into the AN 3n UN plus 1 by 2 AN is 1, so UN. Likewise, you can write it this one. Okay, so that's about Z transform and inverse Z transforms. And then pole zero description of a discrete time system. Given pole zero transfer function or different, how to find any other representation and discuss the system stability with reference. So that's what I told you. If you are given a pole zero diagram, transfer function or difference equation, you should be able to find the other things. So for example, if you are given a pole zero diagram, let's say 1 here and 1 pole, 1 0 here. What is this one? So what is the approximate magnitude response? So yeah, the approximate magnitude response has to be because this is the 0 axis. So at 0, approximate magnitude response, this is a 0 axis. So at 0, it has to be 0. And when the so this has to be at 0 here and it has to go up. Okay, so this is a high pass filter. And here, if we have this kind of thing, if the 0 is here on the unit circle, if the 0 is on the unit circle, then this one has to touch this one. Again, it is a high pass filter. And if the 0 is here, what happens? This is a pi axis, so at pi, it has to be a low value. So this will be a low pass filter. And again for this one, when the 0 actually on the unit circle, the low pass filter becomes likewise, it will touch at the pi. Okay, so that's how, if you are given a pole zero diagram, you should be able to find the approximate magnitude response and also the Z transform. So how do you write the Z transform here from here? So it's Z equal to, so this is the denominator, so that numerator for the zeros, numerator is Z minus, let's assume it is at 0.9, and denominator it is Z. So that is 1 minus 0.9 Z to the minus 1. Likewise, you can write the Z transform also if you are given this one. And if you really want to find the exact magnitude response for this one, let's say this is 1 minus Z equal to 1 minus Z to the minus 1. If you really want to find the exact magnitude response, then how do you find it? You want to find the exact magnitude response, then you replace Z equal to e to the j theta and substitute. So h theta equal to 1 minus e to the minus j theta. So then you can find the so h theta. So h theta, what is h theta is mod of h theta multiplied by e to the j phi theta. Okay. So this is the magnitude response and this is the phase response, both together. So here, then how do we find this one? So one trick is you take out the half power of output here. So from here, what you do is h theta equal to, you take the half power out minus j theta by 2 out. So if you take out this half power, what happens here, e to the j theta by 2 minus e to the j minus j theta by 2. So here you have the sign pattern. So this one e to the j theta, e to the j theta, what is e to the j theta? Cos theta plus j sin theta. So cos theta plus j sin theta, here cos theta minus j sin theta. So both cos theta cancel out. So you get e to the minus j theta by 2, j sin theta by 2. Okay, so here then you will have to break it into this magnitude and phase. So this one has to be magnitude and phase. So then how do you write this j? J equal to e to the j pi by 2. Okay, so why pi by 2? What is cos pi by 2? 0. Plus j sin pi by 2. So this is cos pi by 2 plus j sin pi by 2. So cos pi by 2 0 plus j into 1. Okay, so that is j. So j is this one. And likewise, what is minus 1? Minus 1 is equal to j pi. So here also plus or minus is okay. Plus or minus pi is minus 1. Okay. So here this one has to be in the power. So e to the j pi by theta by 2. Then e to the j pi by 2 sine theta by 2. Okay. So then your phase response, magnitude response is sine pi by 2. What is sine pi by 2? This one, sine pi by 2. So at pi, this is pi by 2, that is 1. Okay, so that is magnitude response. And the phase response is pi by 2 plus pi by 2. Sorry, it is minus. So negative gradient with pi by 2 plus pi by 2. So at 0, it is pi by 2. So likewise. And here it is this one. Likewise. Okay. So here you should remember this is an even function. This is even function. And this phase response is an odd function. Okay. So that's how you find the magnitude and phase response. So when you find magnitude and phase response, be careful on this j term. And also when you have this part becomes minus, then you should be, for example, if you have magnitude response becomes h theta is something like cos theta or cos theta. Yeah, if h theta is equal to cos theta or cos, cos theta, then when you draw the magnitude response, cos 0 is 0, cos pi by 2 is 0. So this is the cos function up to pi. But magnitude response means h theta mod of h theta. So that means this is pi by 2. That means we can't have this part. So this has to be up, okay, mod of h theta. And then this part, this minus, because this is minus, so that minus has to come in the frequency response. So that means this one we can write it as mod of h theta multiplied by e to the j phi theta. Okay, so phi theta becomes 0 when cos theta greater or equal to 0, and minus 1, sorry, not minus 1. So what is minus 1? Equal to e to the j plus or minus pi. So that becomes plus or minus pi when cos theta less than 0. Okay, so this is, you should be very careful. Magnitude response cannot have a negative value. Okay, it has to be positive. Okay, so that's about the magnitude and phase response. And then from transfer hand calculation, magnitude response, definition of discrete time Fourier transform. Yeah, so then the discrete time Fourier transforms. Yeah, so what is Fourier transform? So there are four things. One is Fourier series. Fourier series for a periodic signal, you get the Fourier series as discrete values. So this is the fundamental and there's harmonics. And the continuous time, so then continuous time Fourier transform that you already studied in some other subjects. Here, what we have, so for continuous time means you have xt. From that one, you get xf. So that is continuous time or x omega. So that is the continuous time Fourier transform. Here, when we are studying discrete Fourier transform, discrete time Fourier transform is from xn to x theta. Xn to x theta. So that is equal to xn, you know the equation, e to the minus j n theta. Okay, so this one. So here, this is x theta. And remember this one, this theta is actually a continuous variable. Theta is actually a continuous variable. So then discrete Fourier transform. So that is what you are doing it in MATLAB. So discrete Fourier transform is from xn to, this one is also discrete, xk. Okay, so that is discrete. So xn e to the minus jn. What we are doing theta is, we take the theta into, divide it into n points. Okay, so what is the total value of theta? 2 pi. So that 2 pi is divided into n points, then multiplied by k. So whatever the k equal to 0 to, because since we are starting from 0 to n minus 1. Okay, so that is discrete Fourier transform. This is what you get in MATLAB when you take FFT, that is this one. Okay, so in FFT you have the n, so that capital N is actually this one. Okay, so then if you are to take any DFT for any signal, so if you have any, let's see the notes. So these pole zero diagrams, how to find these things. Okay. Yeah, discrete time Fourier transform. So discrete time Fourier transform also you have all these properties. All these properties you have here. So these properties you have, and so this is how you find the discrete Fourier transform. You replace h equal to j theta. So that is discrete time Fourier transform. And discrete Fourier transform, so discrete Fourier transform is this one. So if you have a simple find DFT of 3 sample average discrete Fourier transform, so then discrete Fourier transform is here. So you take this one 2 pi over n and you find this xk. And here if you have to find the values for this one, then n is given. So if n is given as, let's say n is given as 4, then what you have to do is you substitute these values and find the values of k, h0, h1, h2, h3, likewise you find it. Okay. So that is the discrete Fourier transform. And yeah, and discrete Fourier transform, you have the conjugate symmetry. So if it is 4 point n equal to 4, then what you have is you take the 0 to fs into 4 divisions, and you are finding the values of these 4 points. Okay, so that is the for a. So this one will be x0, x1, and this will be x2. This will be capital X, capital X3. Okay, and these are conjugate symmetry. Okay, conjugate symmetry. It's conjugate. Okay, so these are conjugate, and this will be the DC value. Okay, so that is about discrete Fourier transform. And yeah, so I think I missed a section here with these different types of filters. The summary sheet, let's see. Yeah. So that is about the different types of filters, FAR filters, IAR filters, linear phase. So FAR, you know, doesn't have poles, so only zeros. And some filters you need to know is linear phase filters. One is linear phase filters. Why do you need linear phase filters? Because in music applications, the group delay has to be constant. Group delay. So for linear phase filters, the group delay is constant. Okay, so if it is constant, then the music won't distort, because in music, different instrument will have different frequencies. Those timing has to be maintained. So if the group delay is constant, when you pass through those filters, the timing will not affect. Okay, so that's the linear phase filter. So how do you check the linear phase filters? In the impulse response, the impulse response has to be symmetric. So that is from HN, you can find the linear phase filters. as an impulse response symmetry. And from the pole zero diagram for linear phase filters, the zeros has to be reciprocal. So if you have a zero at this one, let's say R is equal to 0.8, then you need to have another zero with R equal to 1 over 0.8. That is outside. So reciprocal zeros. So if you have a zero here, that zero has to be here and here, here. So these are the linear phase, okay, linear phase filters. And for all pass filters, so all pass filters, the pole zero, in the pole zero diagram, you should have this poles and zeros as conjugate symmetry. So that is the all pass. So all pass filters means the magnitude response is constant. Magnitude response is constant. Okay, so that is all pass filters. All pass filter. So here the poles and zeros are conjugate. Okay. The other one is the minimum phase system, maximum phase system, mixed phase system. So for minimum phase system, all the zeros has to be inside the unit circle. That is for minimum phase filters. And for mixed maximum phase filters, so maximum phase filters, all the zeros has to be outside the unit circle. And something in between, that is the mixed phase. Mixed phase filters, that is, you will have some zeros inside and some zeros outside. Okay, so that is the mixed phase filters. Okay, and that is about filters and recursive and non-recursive filters. So, and also you should be able to know the different type of implementations. One is if you are given the recursive structure, so it's set equal to 1 plus 1 over 1 plus z to the minus 1 plus. So these are recursive. So this is recursive. Recursive means feedback. Non-recursive means FAR. FAR is non-recursive. And then here you should be able to draw the structures, the direct form 1, direct form 2, direct form 1. Direct form 1, you will have the 1 minus z to the minus 1, let's say. So direct form 1, first your feed forward system. First feed forward system, and then your feedback system. Okay, then that is the direct form 1, and direct form 2. Direct form 2, that is, you have this first you have this feedback system, and then you have the feed forward system. Okay, so that is direct form 2, and then canonical. So canonical, your order has to be equal to, filter order has to be equal to the number of delay elements. Okay, so the order has to be equal. So here, what is the order of this one? Order is the maximum power of Z. Order is 2, second order filter. So you should have only 2 memory elements for the canonic system. Okay, so sorry. So for the canonic system, you have this one. So all these things have these values here. And then, so this is the canonic system. And then parallel structure and cascade structure. So parallel structure means you should have this parallel structure. Likewise, and then you should add these things. So if you are given it's a Z transform, then what you to do the parallel structure, what you have to do is you do the partial fraction. 1 plus Z to the minus 1 plus some value here, 1 minus Z to the minus 1. So that is how you do the parallel structure. And for the cascade one, it is the multiplication. Okay. So here, divide by 1 plus Z to the minus 1 multiplied by 1 minus Z to the minus 1. So here it is the cascade structure. Okay, so that is parallel structure and cascade structure. Okay, then let's go on to the filter design. So next important part is the filter design. So in the filter design, so first choice you will have to make is FIR or IAR. So how do you make that choice? So based on the number of, FIR, IAR always less coefficients. This one, the important property of IAR filter is less. So comparatively to FIR, IAR is actually less coefficients. So less coefficients mean less complexity. So it is actually better. But linear phase is not there. Linear phase is difficult. But here, getting linear phase is okay. Linear phase is okay. So if we need linear phase, we go for FAR. Otherwise, we go for IAR because of the computational complexity. Okay. So that is about filter design. And then you should know about the IAR filter design methods and the FAR filter design methods. So two methods are there for IAR. One is impulse invariant transform. So what is impulse invariant transform? You keep the impulse as it is. So that's how you get the impulse invariant method. So in the problem with the impulse invariant method is aliasing. Aliasing is the problem. So for low pass filters, it is okay. And how can you solve this impulse invariant problem? By increasing the FS. If you increase the FS, then the aliasing problem becomes less, so it can be okay. Then the next method is the bilinear transform. Okay, so for impulse invariant transform, you have one the transform that you can quickly replace this S. So that is in the notes, you can quickly find it. And for the bilinear transform, so bilinear transform is a little bit tricky. I will go. For bilinear transform, what you have to do is, because infinite, because analog frequency is from minus infinity to plus infinity. This is analog frequency, but digital frequency theta is only from by fs by 2 pi to minus pi. Okay, so then we do this mapping, tan H mapping. So because of this mapping, so there is a warping. So warping effect is there. So to have this warping effect, so for example, if you are to design a bilinear transform method with a transfer function of S plus 1, and if the cutoff frequency is digital frequency, remember this one, digital frequency specification. Digital filter specifications. So Fs is given 1000 Hertz, and FC equal to, let's say, 100 Hertz. So here it is the digital frequency. So digital frequency. Okay, remember this one, these are digital frequency. Then the first step, step one is you will have to have the analog filter. Analog filter. So you need to get the analog filter. So you need to design the analog low pass filter. So for that one, you need to know the analog cutoff frequency. So how do you find the analog cutoff frequency? Because here we, for each analog filter frequency, this digital filter frequency. So each digital filter frequency is warped to, sorry, each analog filter frequency is warped to an analog digital frequency. So you need, first step is you need to find the pre-warp analog frequency. Okay, so that is the first step. There's an equation, so I will quickly go to show the equation for the pre-warp analog frequency. Yeah. So for pre-warp analog frequency, those equations, you can quickly find it. The mapping equations. So remember not to get confused with these two equations. There is warping equations and pre-warping equations. So this is the pre-warping frequency. So here this is the filter. So 2/2 tan theta by 2. So here, so what we have to do is the pre-warp frequency. So that has to be, that is 2/t tan theta c. What is theta c here? This is 100. So 2 pi. So theta c is, you can find it here, 2 pi 100 divided by 1000. So that is theta c by 2. Okay. So that is the pre-warp frequency. And this one, this has to be greater than, so this is what you are getting is 2 pi omega dash c. So that is equal to 2 pi fc dash. Okay. So here, as a check, if you find this fc dash, or that is the pre-warp frequency, fc dash has to be greater than fc. Okay, so that is a quick check. If your fc dash, if your pre-warp frequency is less than fc, then something is wrong. Why? Because this frequency, this analog frequency is always higher than this digital frequency. Okay, so that is the first step. Then what is your second step? Step 2. Step 2 is denormalizing. Okay, so denormalizing. So then step 2 is denormalize it. Denormalize it. So S becomes S over omega c dash. Then step 3, you replace that bilinear transform equation. That S equal to, you know that's equation. So this equation, 2/t, so 2/t, z minus 1 over z plus 1. Okay, so that is how you do the bilinear transform. And for impulse invariant transform, step 1 is you do the denormalizing. If you are given the cutoff frequency, then you substitute. Okay. So those are very simple. Okay. Then the other one is the FAR filter design. So FAR filter design, windowing method. FAR filter design, windowing method. So what we do is, if you are given a magnitude spectrum, let's say if you are given a simple magnitude spectrum like this. So this is, let's say, theta c. This is pi. So then what you do is you take the inverse Fourier transform and you find Hn. So first you will have to find the Hn, inverse Fourier transform. So how do you find the inverse Fourier transform? Inverse Fourier transform 1 over 2 pi from minus pi to plus pi. This h theta. So this is h theta. So this is actually mod of h theta. Okay. What is mod of h theta? What mod of h theta is the magnitude response. So magnitude response. And what is the phase response? Phase response, we already know e to the j phi theta. Okay. So phi theta we already know, because for phase response it has to be linear phase, because linear phase we go for FAR design, FAR filter design. So that means phase response has to be linear phase. Okay. So e to the minus j b theta b beta. So this is equal to e to the minus j beta theta, and beta is your number of filter order, because filter order n will be given, n equal to 7 or 9 or whatever it is given. So this beta will be n minus 1 by 2. Then you know the phase response. So you can actually do it in two methods. One thing is you can keep here your mod of h theta e to the j n theta d theta, and you can integrate it to find it. That is one method. The other one is, that other method is, you can have this. Then if you have this one, then what you need to do is you will have to flip to bring it to 0. So maybe I will, if I do this one, it will take time. So what I do is, here what you do is, maybe I will quickly do it. So then 1 upon 2 pi. So theta c, let's say pi by 4. So minus pi by 4 to plus pi by 4. This is 1 e to the j n theta d theta. Okay, so that is equal to 1 upon 2 pi. So integration, what is integration of j theta? 1, so e to the j n theta divided by j n, here pi by 4 to minus 4 to plus pi by 4. So this one is when n not equal to 0, because otherwise n becomes 0. Okay, so that is equal to 1 upon 2 pi. So e to the j n pi by 4 minus e to the j n pi by 4 divided by Jn. Okay, so that is equal to, so this one, what is this one? This is sine theta, so 2j sine theta, so 2j sine n pi by 4 divided by 2 pi jn. So here this j become cancel out, 2 become cancel out, so that is equal to sine n pi by 4 divided by pi n. So sine n pi by 4 divided by pi n. So that is equal to sine n pi by 4 divided by pi n. So again, that is not equal to 0, n not equal to 0. So when n equal to 0, what you can find it from the L'Hospital rule. So here n equal to 0, sine n pi by 4 divided by n pi by 4. So then 1 over 4. So this part is equal to, when n equal to 0, this becomes 1. So that is sine n pi by 4 divided by n pi, and here 1 by 4. This is for n not equal to 0. This is for n equal to 0. Then when you plot it, let's say order is, capital N is less, let's say capital N is 5 points. Then the first point, this one is 14. So this is actually H desired end. This is what we prefer to have have this one. But then we will have to Hn, we will have to multiply by Hdn multiplied by, not convolution, multiplied by Wn. Okay, so here Wn can be any window, that Bartlett window, different windows have different equations. So if the equation is given, you substitute and find it. If it is rectangular window, then it is 5. Sorry, it is just 1. So if it is 5, then you will have only 5 coefficients. So what are the 5 coefficients here? How do we find this one here? So this one, so this 1 by 4. Then the second point, n equal to 1. So sine pi by 4 divided by pi. Then n equal to 2, sine pi by 4 into 2 divided by 2 pi. So then we have to make, because remember that here, the previous one, we start with the magnitude response. We did not have a phase response. Remember, we did not have a phase response. So that means we did not impose the phase response, linear phase condition. Here we have to impose it. So how do we make it? So we can make it as a linear phase, because for linear phase, we know the impulse response is symmetry. So what we do is we bring this one here, bring this one here. So sine pi by 4 by pi here, and sine 4 into 2 by 2 pi. So then this is linear phase. This is actually method 1. Okay, so this is method 1. Okay, and you can do it another way. That is method 2. Method 2 is you put the Hn, H theta, e to the j n theta, d theta, integration 1 over 2 pi, Hn, Hdn. That is equal to, here what you do is 1 upon 2 pi minus pi to plus pi. So for h theta, 1 into e to the j minus j beta theta, e to the j n theta d theta. Here you impose this beta equal to 5 minus 1 by 2. Okay, if you go this way, then you will directly get that shifted equation. Okay, so this is method 2. Here you put the phase response, there you don't put the phase response. Both methods are okay. Okay, so that's about the filter design, and I will quickly go through the multi-rate signal processing. That is the last section. So for multi-rate signal processing, you have this downsampling. So what you have this signal here, fs by 2, fs equal to, let's say, 8,000 hertz, 8,000 hertz, and you are going to upsample it to fs equal to 16,000 hertz. So that means here for each second you will have 8,000 samples. Here you will have 16,000 samples. Sorry, down samples. I'm sorry. So what we are doing is downsampling. So downsampling means reducing the sampling frequency. So we are bringing it to 4,000. So we do the downsampling. So that means we have to remove the samples. So we have to remove one sample here. So for the downsample, so the magnitude spectrum, let's say if we have the magnitude response up to 4K is like this, then after downsampling it, we can have only up to 0 to 2K. Okay. So then we will have the problem of aliasing. So to prevent aliasing, we have this filter. So if we have the direct downsampling, we have the aliasing. So to prevent downsampling, we put a filter first, and then we do the downsampling by 2. So what should be the cutoff frequency? So the final signal, we know we can only have up to 2 kilohertz. So anything higher than 2 kilohertz need to be removed. So the FC will be 2 kilohertz. Okay, so FC will be 2 kilohertz. And the theta C, what is the theta C? Cutoff frequency theta C, that is 2 kilohertz. So what is the FS here? FS is 8 kilohertz. What is the FS here? Again 8 kilohertz, because filter will not change the sampling frequency. Only here fs equal to 4 kilohertz. Only here it is 4 kilohertz. So here downsampling by 2. So that sampling frequency 2 kilohertz, 2K into 2 pi divided by fs. What fs here? It has to be 8K. So what is this one? 8K, so 4 pi by 2. Okay. So pi divided by this downsampling factor. This factor is pi divided by downsampling factor. So that is the cutoff frequency. So that's how you do the downsampling. So what happened to the magnitude response? For this downsampling case, what happens to the magnitude response? So initially you have this one up to 4K. Then you have this low pass filter. So after low pass filter, -4. After low pass filter, what you have is only up to 2K. Here again, -2K. Okay. Then you have this this one after downsampling it, downsample by 2, you get it as this one 2, then this mirror image up to 4. Likewise, it continues. Okay, digital spectrum, you know, it continues, but 2K. And here, this one, if we draw it in the theta axis, so here we are drawing it in the Hertz axis. Frequency is Hertz. Okay, frequency is Hertz. So if we are drawing it in the theta axis, what happens is this one is theta is pi, theta is minus pi. So after this one filtered, this one, what happens is this is pi by 2, and up to pi it is 0. This is pi by 2, then it is 0. Okay, minus pi by 2, minus pi. And after downsampling, the final one, after downsampling, this one become, this point become pi, minus pi. Okay, sorry. So this part is stretched. Here it is stretched. This part is stretched. Stretched. Yeah. Stretched. Okay, so this is stretched. Okay, so this is stretched. So that so this becomes stretched. So how do we do the downsampling? We take out the alternate signal and we do the downsampling. So in the downsampling case, we have this low pass filter here. Okay, so that is for the downsampling case. And next, we look at the upsampling. Upsampling. So let's say 8K, we have 8K. We need to bring it to 16K. So how do we do the upsampling? So here, let's say the spectrum is like that, 0 to 8K, sorry, 0 to, if the sampling frequency is 8K, then the maximum frequency we can have is only up to 4K. So this is minus 4K. Then we know that in this spectrum is actually repeating 8, 12, like that. Okay, digital spectrum repeats, but even though it repeats, this is the real frequency content. This is the real content. These are imaginary. All these contents are imaginary. These are imaginary. 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 Okay. So then when we upsample it, if we make the sampling frequency to after this upsampling by 2, after this upsampling, what we have is the same spectrum, but now our F becomes 16K. 16K means up to 8 kilohertz. Sorry, this one, this is not 8, this is 8. So this is 4, this is 8K, this is 12K, like that. So this is 8K, this is 4K. Okay. So here, as I told you earlier, this is the real one, but this also real in this case. Real part. Why? Because the FS is 16, so 8 is 16 by 2. So this is the real part area. But we already know that this part cannot be real. Cannot be real. Why? Because it is not in the original signal. So we can't have any additional signal. So that need to be removed. So that is why we have a low pass filter. To remove that one, we have a low pass filter. So to remove that one, so after removing it, we have up to 4 kilohertz, we have this content. Then we have 0 up to 8 kilohertz. Okay, so then that is the final signal. So what is the cutoff frequency here? This one, what is the cutoff frequency? FC, what should be the cutoff frequency here? The cutoff frequency has to be 4 kilohertz. Why? Anything higher than 4 kilohertz, we have to remove. Okay. And what is the theta C in the digital frequency? 4K into 2 pi divided by Fs. What is the Fs here? Fs is 16K. 16K. So that is again pi by 2. Okay. So the block diagram is, so the block diagram for upsampling is, first you have to do the upsampling, then you need to do the filter, low pass filter. And the low pass filter cutoff frequency, so here 8K, here it is 16K. So low pass filter cutoff frequency is 4K, because here this is the, in this signal we know, the maximum frequency we can have is 4 kilohertz. So we cannot have anything higher than 4 kilohertz. So and theta C is pi by 2. Okay. So that is about upsampling. And the third case is if we have a non-rare, so 8K to 12K. How do we do? Then how do we do 8K to 12K? So we have to, first we have to do the upsampling. What is upsampling? 8K to by, so 8K we can upsample it by 3 to 24K. Then if we upsample it, then we need to have a low pass filter. Then we can downsample it to by 2 to get 12K. Okay, so what should be the low pass filter cutoff frequency? So for this upsampling part, what we need to do is, for upsampling we need to have a for this upsampling part we need to have a low pass filter. We need to have a low pass filter. So this low pass filter, what is the cutoff frequency? FC is 4K cutoff frequency. Okay. After that, again for this downsampling, we need a low pass filter. So here, what is the sampling frequency here? 24K. So from 24K, we have to bring down to 12K. So here, what should be the cutoff frequency of this one? 6K. Why? Because here we cannot have anything higher than 6K. So 6K, higher than 6K will get ADA. So we need to have a cutoff frequency of this one. So here you can see that we have a low pass filter with 4K and 6K. Is it meaningful? If we have a low pass filter with the cutoff frequency of 4K, then do we need a filter with the 6K? We actually do not need this filter. We do not need this low pass filter. So this low pass filter we do not need. Okay. So this low pass filter we do not need. So we can actually remove this low pass filter. So then our final block diagram will become this 3 upsampled by 3, then a low pass filter with cutoff frequency of 4 kilohertz, then downsampling factor 2. Okay, so what should be the cutoff frequency of this one? What should be the cutoff frequency of this one? quickly go through. So first upsample by 3, low pass filter, downsample by 2 to get it to 12K, 8K here. So here 24K, and here again 24K. Here it is 12K. So what should be the cutoff frequency? Cutoff frequency is FC is equal to 4K. So what is the theta? 2 pi 4K divided by what is the sampling frequency? 24K. 4K. So that is equal to 8, so pi by 3. Okay. So that is the cutoff frequency here. So that is for the conversion from 8K to 12K. Okay. So that is with multi-rate signal processing, and there is a small section modulation also. You have this modulation. Sometimes you will have this modulation and downsampling. And so modulation, like let's say modulation. So modulation, what happens? You have the signal here, xn, and here cos theta naught n. So when you do the modulation, what happens? X theta is, if you have x theta something like that, pi minus pi. What do the, it's not pi, let's say. Let's say pi by 4 minus pi by 4. What modulation do is, modulation is actually shifting it. So it's shifted to theta c and minus theta c. Okay, so it shift. That is the modulation. So theta, so this is pi by 4, so theta c plus pi by 4, and this is theta c minus pi by 4. Okay, so that is the modulation. Okay, so I hope I covered most of those content. Let's check the summary sheet whether if we miss anything. Cascade parallels, 3 dB. Yeah, 3 dB cutoff frequency. I quickly say about 3 dB cutoff frequency. Another thing is about the 3 dB cutoff frequency. So if you are given h theta, how to find the 3 dB cutoff frequency? So that cutoff frequency theta equal to theta c, that should be equal to half the power modulus has to be half of h theta equal to 0, that power. Okay, so 3 dB cutoff frequency means if it is a low pass filter, so your gain is somewhere here A, this is h theta, what of h theta, then this place where A by root 2. So here it is the magnitude and here it is the half power point. Okay, so that is the theta c. Okay, And another thing I wanted to say is the filter specifications. So if you have this one filter, so remember this one. So what are these specifications? So this is the gain. So this is the stop band attenuation. This is the stop band attenuation, and this is the transition band. So this is transition band, and this is the stop band ripple, and this is the stop band attenuation. Okay, so this is also about the filter specifications. And let's say whether we have missed anything. Minimum, maximum phase filters. Yeah, another thing is this one. So when you reflect a zero, from here to outside the unit circle, let's say this is R, this is 1 over R. If you reflect a zero outside the unit circle, the magnitude, no change in the magnitude. Change in magnitude response. Okay. Magnitude response, no change. It will be the same magnitude response. That's how we change from minimum phase filter to maximum phase filter. We can simply take the zeros outside the unit circle by flipping it 1 over R. Okay, so that is one thing. And yeah, I think that's all. Summary sheet 5, whether we missed anything. Notch filter. Yeah, the resonators, notch filters. Yeah, that section we missed it. Oscillators. Yeah, I think that we quickly go through that one. The resonator. Yeah, resonators and oscillators. So here, maybe I will quickly go through these notes. So resonator is something that actually resonate. So when you have conjugate poles, that's the resonator. And these resonator transfer, all these things are given here. This bandwidth, how to calculate the bandwidth. You can calculate the bandwidth like that. And notch filter. Notch filter is when you have this resonant poles and a zero closer to that one. So that will bring the notch filter to like this, to 0. And you can find the equations. This is the R equation and the bandwidth equations. So you can find the R and bandwidth. So it is the notch filter. So when you have these two poles, then your filter becomes peak there. But when you put these zeros here on the same angle, the same theta angle, then that becomes that at that point the frequency is taken out. So that is the notch. And if this cutoff frequency is given, this theta c is given, then you should be able to find R. Okay, so you need to know the relationship between R and theta c. So that is given here. So delta F is the cutoff frequency. So delta F is the deviation, so plus or minus deviation. So then if you know that one, you can calculate the R. So that is with this R, you can write the difference equation. So when after you find these poles and zeros, you can write this transfer function. This is easy. So you can quickly write the transfer function. So here, this is the zeros, and these are the poles. Okay, so this is 0, 0, and these are the poles, and you need the pole radius. And both angles are same, 0.2. And you calculate the angle using this merge frequency. Okay, so that's about this merge filter and this stability triangle. That's okay. And the digital oscillator, just remember one thing, that you can make the resonator working with. One is with the impulse input 0, but you need to have these initial conditions. Initial condition, this one and this one. You need to have the correct initial conditions. The other one is you can keep the initial condition 0, but give the impulse as the initial condition. So those are the two ways you can have the. Those are the two ways you can have the oscillators. Okay, making oscillator working. And also you should know the sine single oscillator and the simultaneous oscillator. There's another simultaneous oscillator. This is the simultaneous oscillator. This operate, give cos and sine simultaneously. Okay. Okay, so I hope this will give you a brief crash course on the DSP. So we will conclude. So I will stop the recordings and so Raymond, so we'll stop it. Okay, we'll finish it.
Okay, great.
Yeah.
It's not recording.
Yeah, I will. Yeah, stop.